In the last video from Unit 2, we looked at augmented coefficient matrices, how to set them up, and how they are starting to lead us to finding solutions to systems of equations. When we created the augmented coefficient matrices right out of the system of equations, they were kind of a mess. They were full of lots of constants, and so we're going to learn about a little hierarchy to the structure of augmented coefficient matrices. We will talk about things called row echelon form and reduced row echelon form, and then learn how to read solutions to systems out of those row echelon forms. So here we go. You've got a coefficient matrix, an augmented coefficient matrix. And from this point on, whenever I say matrix in these slides, what we're looking at is an augmented coefficient matrix. And frankly, any matrix you can write down is an augmented coefficient matrix for some system of linear equations. So there you go. We don't necessarily need to make that distinction anymore. But an augmented coefficient matrix, or just a matrix, is in row echelon form, abbreviated REF, if you look at a row, the first non-zero number you see is to the right of the first non-zero entry above it, which sort of gives a diagonalish looking trail of leading non-zero entries. And if you have a row of all zeros, it's down at the bottom. Okay, so here's four matrices. Take a look. Which ones do you think are in row echelon form? If we look at the first one in the upper left, well, just for practice, that would be a system of three equations and three unknowns. In the first row, the first non-zero entry is 2. Then in the next row, it's 1. Then in the next row, it's 2 again. And each one is to the right of the one above. Okay, so we're good. In the second matrix, the one in the upper right, first non-zero entry in the top row is 1. In the second row, it's 1. And in the third row, it's 2. But the non-zero 2 in that third row is not to the right of the one that's above it. They're in the same place. So this is not in row echelon form. In the second row of the matrices, so the two smaller ones at the bottom, both of those are in row echelon form. For the last one with the row of all zeros, that row is at the bottom, and there's only one row above it. There's a non-zero leading one. That's fine. It is row echelon form. So of these four, only one is not in row echelon form. Now we can get a little bit better with our row echelon forms if the leading non-zero digits all happen to be 1. It turns out that's a nice thing to happen when we get to the final solution process. Now remember that any row in a system of or any equation, right, even if it's in a system or not, we're allowed to do anything we want to that equation as long as we do it to both sides. In particular, we can multiply both sides of an equation by a constant. In a coefficient matrix, an augmented coefficient matrix, every row of numbers represents the coefficients from a linear equation. So just like we're allowed to multiply any equation on both sides by a constant, we can multiply any row in a coefficient matrix by a constant and not change what the solution that's buried in that coefficient matrix is going to be. And so what that means is if we see an augmented coefficient matrix like this, we look at those leading non-zero terms, which are 2, 1, and 2. Hooray, one of them is already a 1. The other ones are 2. And in our solution process, which we'll see in the next video, you'll look at that and say, gosh, I wish those were 1s. Can I turn them into 1s? And the answer is yes. You divide the top row by 2, and you divide the bottom row by 2. Okay, technically we're doing multiplication by 1/2 because we're really talking about multiplying a row by a constant, but multiplication by 1/2, division by 2, we're all friends. We'll call it the same thing. Now notice what we did when we changed that first row, when we multiplied it by 1/2 to change the leading coefficient to a 1. We did introduce a couple of fractions, and then in our problem solving process in the next video, that's sort of a decision point that is it worth introducing the fractions in order to produce the 1 in that leading spot, and the answer is sometimes it isn't, but remember that you can do it. The third row cleaned up nicely. We changed it from 2, -2 to 1, -1 through that multiplication by 1/2. Okay, so let's suppose we have a coefficient matrix that does happen to be in row echelon form. At this point, we are ready to back out what the solution to the corresponding set of equations is, and we can do that at this point through what's called back substitution, which you have done before with equations just in the old equation setting. So from what we've already learned, you can look at that last row in the coefficient matrix and understand that that reads for us the equation z equals -1. That's what those numbers tell us, and that's assuming the variables are named x, y, z. Okay, well, if z equals -1, back that up to the second row. The second row's coefficients and right-hand side tell us we're dealing with an equation which currently reads y minus z equals -2. But we already know that z is -1, and so now we can back out the value of y that's in the solution set. And now we can carry this information up to the top row. The top row tells us that x minus 1/2 y plus 3/2 z is equal to 2. And since we're carrying along the discovered values of y and z, we can plug those in. And I'll do this fast. You can back through and make sure it works. That shows us that x equals 2. And so the solution set to this system is 2, -3, and 1. So reduced echelon form is good for our augmented coefficient matrices, but even better, as we've already discovered in the last video, is a coefficient matrix that looks like this. Lots of ones on the diagonal, lots of zeros everywhere else, and numbers on the right-hand side, because that one we can read out. X equals A, Y equals B, Z equals C. This is called reduced row echelon form. This is sort of the gold standard of augmented coefficient matrices. So it's a matrix that's in row echelon form with a couple of extra stipulations. The leading coefficients are all 1, and where you do find those ones, they are the only non-zero entry in their respective columns as well. Meaning, again, 1 sort of down the diagonal, lots of zeros everywhere else. When we have that, the solution to the system is evident. Like that one. Take a look at the second one. That's pretty easy. It's just a 2x2 system, right? So that's easy. Here's another example. Uh-oh, this one's got an interesting wrinkle in it, right? The top row of this new one is telling us x equals 2, because that top row says 1x plus 0y equals 2, so x equals 2. That second row is a puzzler, because that says 0x plus 0y equals 1, which can't be true for any x and y, because then we'd be concluding that 0 equals 1. Well, that means this system had no solution. Remember, there are 3 scenarios: a unique solution, no solution, infinitely many solutions. Here we came up with a visual cue in the coefficient matrix that our system has no solution. So weird things can happen. Here's a different strange thing that can happen. This system would read for us 2x plus y equals 3, and the second row reads 0x plus 0y equals 0. Now, unlike the last page, here the bottom row is actually true. 0x plus 0y equals 0 is true, but it's true for every x and y. So it's true, but it's useless in terms of information, because there's no information there to help us determine either x and y, because that row is true. It's always true, and so it's not helpful. The top row tells us that 2x plus y is 3. That's all we know about this system. We have 2 variables to resolve, and the only thing we can get is a relationship between the 2 variables. We can't resolve one or the other one of them in particular. And so what we might do is say, we just have to pick, what one of the variables. We'll just say it is what it is. It's going to be x, right? X will always be x. We can't pin it down. But once we have a value of x, there has to be a distinct relationship to what the y value is, because 2x plus y has to equal 3. So given any selection for x, the y value has to be 3 minus 2x. That means we have an infinite number of solutions, and we have a little recipe for how we can describe those solutions. Infinite number of solutions doesn't mean anything is a solution. There's still particulars to it, and we have to be able to describe those particulars. So the 3 scenarios that we've talked about multiple times: unique solutions, no solutions, infinitely many. The row echelon forms, and particularly the reduced row echelon forms, will have clues for us in there about what's going on, and we have to learn to recognize them. So here's a little bit of practice. Augmented coefficient matrix in row echelon form. What do you know about the solutions? Well, take a look at that last row. There would be 3 variables here, so this last row says 0x plus 0y plus 0z equals 1. That is nonsense, no matter what x, y, and z are. So there's no solution to this system. Here, now we have a row that is all zeros, which means 0x plus 0y plus 0z is 0 is one of the equations in this system at the moment. That's always true for any x, y, and z, so it's always true, it's always useless. for our hunt for a solution. This system has 3 equations and 3 unknowns. One of those equations isn't going to provide us any useful information. The third row is generally where we would look for values for z, the third variable. We will say, we're not going to be able to pin z down. Let's let z be anything. Z will just be z. Move that up to the second row. Well, y minus z still has to be 2, so there is still the relationship between z and y. And then bring that up to the first row. Since z affects y and z and y both affect x, we can complete that trail and find out that x is also related to z. So we'll never pin z down. But once a value of z has been picked, like z equals 5, then we would know that the corresponding y value has to be 7, and the corresponding x value would have to be, well, whatever that yucky thing gives for z equals 5. But there is a prescription for the solution set. There will be an infinite number of solutions, and there is a relationship between the variables that has to be prescribed. Okay, so if we have augmented coefficient matrices and they are given to us, or we can put them in row echelon form or reduced row echelon form, we're in really good shape for finding the solutions. The only thing left to do is discover how we put our augmented coefficient matrices into these row echelon forms. That is something called Gaussian elimination. You have already done this before, believe it or not, and that's what we're going to see in the next video, which is the last video for this unit.